Algebra-based physics, electromagnetic induction. We'll start with electromotive force, very similar to voltage. It is a bit of an archaic term, but it's still used for historical reasons. Magnetic flux, very key definition here to understand flux. Then we'll go through Faraday's law of induction, Lenz's law, the EMF, which is electromagnetic force induced in a moving conductor, and finally, we have several problems, free response problems, solved out in detail. We'll begin the discussion by defining induced EMF, where EMF stands for electromotive force. Electromotive force is actually a potential difference between 2 points. It is measured in volts. It is not a force. However, historically, that's what it was named, and the name is just sort of kept on going. However, because it really isn't a force and the name isn't the greatest, it's frequently just referred to as EMF, or the Greek letter epsilon here, capital epsilon. It basically represents the voltage developed by a battery. We talked about that last chapter when we had the terminal voltage of a battery is equal to its EMF minus the current times the internal resistance. Now we're going to show another way a voltage can be developed in a current carrying wire, but without a battery. Ørsted and Ampere both did experiments that showed how a current will generate a magnetic field. After this discovery, physicists who are always looking for symmetries wanted to see if the reverse could be true. Could a magnetic field generate a current? Michael Faraday was able to make this connection in 1831. At the same time in America, Joseph Henry performed a similar experiment but did not publish it. This happens a lot in mathematics and physics. Probably the greatest example is Sir Isaac Newton in the UK and Gottfried Leibniz in Germany developed related forms of calculus at the same time, independent of each other. This was Michael Faraday's setup. He connected a battery with insulated wire, wrapped it around this metal core, and this metal core is there to maximize the magnetic field. But this is an insulated wire, so at no time did any current pass from the battery into this ring here, this coil. Then he took other insulated wire, wrapped it around, connected it to an ammeter. And again, there is no connection, no physical connection between this side of the circuit and this. He then closed the switch. He noticed a momentary spike in the current on the right side here, which then went to zero as he left the switch closed. When he opened the switch, he saw the current spike in the other direction and then go to zero. So when this current on this side was steady or zero, no current showed up here. However, when the current changed, then you would have a current. Here are a couple of other ways of looking at this phenomenon. Faraday also built this thing called a Faraday's disk generator. You have a metal disk here, and over here you have a U-shaped magnet, so there's a magnetic field between these two poles. And here's a handle here. You would spin this disk. So what happens as the disk goes through the magnetic field, any point, let's take a point here, it would have a maximum magnetic field over here, and then as it moved away, the magnetic field would decrease, and then increase it again as it gets near the pole. What was found is by spinning this wheel, you have two connections here, see this little guy B prime and B, you would connect those via wire to an ammeter, and you would read a current. So what we have here is you're turning a wheel with your hands, putting mechanical work into the system, and generating an electric current coming out over here. Again, you see no battery here, you just see a magnet and a spinning wheel. A little more simply, if I had a magnet, here's a little bar magnet, north and south pole, as I move it towards or away from the circular loop of wire, if I had an ammeter connected up to this, it would read a current when the magnet was moving. Soon as the magnet stops, the current would go away. Let's summarize what we've seen via experiments. We have evidence that a magnetic field can generate a current. But there is a difference between what a current does when it generates a magnetic field. A steady current will generate a magnetic field. But if you have a steady magnetic field and a non-moving loop of wire or a disk, like we showed in Faraday's disk generator, you will not get a current induced in the other wire. A constant magnetic field, though, in a moving loop of wire will result in a current. That's Faraday's disc generator. We had a constant magnetic field, but we were spinning that disc inside the magnetic field. Also, a changing magnetic field and a stationary loop of wire will result in a current. That was Faraday's first experiment with the iron core, where you had the changing magnetic field because you turned a circuit on or off. So when the current was flowing, you had a magnetic field. When you turned the current off, the magnetic field collapsed, it changed, and there was a current showing up on the other side of the wire. Now, before we can totally understand this and before we're ready for Faraday's law, we will have to define magnetic flux, and that will be done in the next section.